So, it's my honor and my pleasure to present to you, yes, Professor John Mumma from the University State of California, San Bernardino. John is here through a project that we submit to CNPq and also with the aid of the Programa de Pós-Graduação em Filosofia, da URGS. Well, John Mumma has been working in postgrad mathematical practice. It's been a long time now, and his major contributions are in the field of philosophy of geometry and of diagrams. Hope you enjoy the talk. John, it's very nice to have you here.
It's very nice to be here, and it's very nice to see so many people for a talk on diagrams. It's also nice to have the sun, I've been told. It's been raining here a lot, so it's beautiful here. Okay, so yeah, again, it's great to be here. The first slide I want to start off with to give you the general idea of the talk. I want to compare these two proofs. These are both proofs of the same proposition, and they're very close as proofs. The proposition is from the Elements, proposition 33. What it's saying with this proposition is it's a very simple geometric proposition that if you know that these two segments are parallel and equal, then you know that these two segments are parallel. Okay, so this is the proof. And, well, this is the proof as you see it in the Elements or in Heath, in the translation, the English translation. And on the right, what you have is the same information, but the information that's in the diagram is presented in sentences. And so, in a logical sense, they're equivalent because all the same information is there. So the difference is a difference in notation, how certain information is presented. And the claim, the highlight here is meant to show how everything else is the same in black, but what's different is what's highlighted there. And so that's the difference in notation, diagrammatic over here, sentential over here. But the idea is you could look at it as they both represent the same propositions, the same geometric propositions. So in a logical sense, they're equivalent. And the difference is in notation. The claim I want to defend is that this is a proof, and this is not a proof. You destroy the proof once you change the notation. And this is a dramatic claim because, or I don't know if it's dramatic, but it seems not one that people say too much because notation is usually thought to be not essential to the proof. What's important to the proof is the content as revealed by logical analysis, and how you present that content is not important. So I'm going to try to make the claim that it is important, and with respect to this example, you lose the proof once you present it in a different way. So the talk will have 4 parts. The first one, I'll just talk about how, if you look at the elements, the propositions, what a logical analysis looks like. So you take the proposition of the elements, you take the proofs, and you perform a logical analysis. What's the general character of that? What's the picture of the elements that you get when you do a logical analysis? The second part is the work that Giselle just referred to. I'll talk about an analysis of how diagrams are used in the proofs. The work I've done on that with others. So that's the second part. The third part, then, I'm going to bring in Wittgenstein. I don't know much about Wittgenstein, but I like this section, and it seems relevant to my point. And so I'm going to give my understanding of what he's saying. In the third section, the remarks of the foundations of mathematics. In this section, he talks about proof and notation and the relationship. So with that in the background, then finally I'll get to the proof I just showed you, and I'll compare them. All right, so first, logically analyzing the elements. So you have many books in the elements. I've only listed the first 2. They go up to 12, I think. I should know. But I only actually done a work on the first 4. The first 4 are before the theory of ratios, and it's more logically sophisticated once you get to the theory of ratios. But you can be first order from books 1 through 4. And so just suppose it's just, this goes up to book 4, say. If you're going to do a logical analysis of this mathematics, it's from the point of view of mathematics and the history of mathematics up until the end of the 19th century, this was the ideal of formal, rigorous, axiomatic treatment But at the end of the 19th century, you have axiomatizations of geometry coming up when they thought the idea was that this is still informal. It's not formal enough, or it's not logically clear enough, despite the fact that Euclid was developing the geometry in an axiomatic way. You could do better, that the idea was. And what you do, you create an axiomatization. Again, as I just said, the elements develops geometry in an axiomatic way, but it was a more formal way of approaching things in the end of the 19th century. And what you do, first you want to isolate the primitives of the axiomatization, your primitive language. And then once you isolate that primitive language, you use that primitive language to express all the other propositions via those primitives and maybe definitions. So I haven't listed the primitives here, but there's things like point, line, and plane, congruence of angles, congruence of segments. And the idea is once you choose those, you can choose those primitives, you can take all the propositions and then rewrite them according to the formal concept, the concepts that you've isolated as primitive, but also maybe definitions, logical definitions in terms of those primitives and logical constants. Because that's the first thing. The second thing, then you lay out your axioms and you show that everything that you've reconstructed within the axiomatization with the formal language, you can deduce from these simple axioms. Okay. So that, we're familiar with that? You've seen this before? Okay. The one observation I just want to make about this right away is that something that doesn't seem to be talked about too much when you do this kind of analysis, one of the ideas here is that you're actually getting to the essence of the mathematics, to the proof, which is not so formal. I mean, it's in the informal version, you get a certain idea of it, but to really get a sense of what the logic of the proofs are, you have to do something like this. But one thing that does happen when you do that, you don't just get as theorems everything that you already had as theorems. You get this, from the point of view of this analysis view, just within this box, anything that's a logical consequence of the axioms is a theorem. Anything that's true within the models, so you look at it in the model theoretic way, anything that's true within the models of the axioms is a theorem. So you lose, like in an informal sense, there's only certain things that have been identified as propositions. But in the axiomatization, you get a lot more statements that are theorems. So something that might be trivial from a geometric perspective. The fact that, I don't know if you can read it, if you have a quadrilateral, you take the diagonals, they intersect. It's not a theorem in Euclid. It's something thought to be trivial. You don't have to prove this. He makes use of this fact in his proofs, but he just takes it for granted. So from the point of view of Euclid, that's trivial. But from the point of view of the logical analysis, it's still a logical consequence of the axioms. It's a theorem. Also, any arbitrary conjunction of propositions will be a theorem, because again, it's a logical consequence of the axioms. But from the point of view of just the geometric perspective, Euclid's geometric from the perspective of Euclid's geometry or his geometric perspective, this is more not one individual theorem, but it's just a listing of three separate theorems. So the point is just that the issue I want to bring up here is just the individuation of theorems and how if you perform a logical analysis, you lose that. Because within a logical analysis, your only conceptual resources are what's a logical consequence of your axioms. And everything that is a logical consequence ends up being a theorem. So you might not find this interesting. I hope you do, because I'm going to talk about it in a little next few slides. And then I'll argue why this might be philosophically relevant. You could just respond, well, if logic doesn't pick it up, it's not philosophically relevant. But I'm going to talk about now how you can actually give a story of how these theorems are individuated. But what you have to do is you have to look at how the theorems are proved with diagrams. So first, just go through an example of such a proof. This is proposition 5 from book 1. All isosceles triangles have equal base angles. So the proof starts off with a triangle. Let ABC be a triangle. You extend the side AB to D and the side AC to E. And then you pick an arbitrary point on BD. And then construct a point G on CE equal to BF. Or it could be AG as well, and AF. Then you join those two, create those two segments by joining B and G and C and F. Okay, so that was the construction. What I just showed you was what's called the construction in a Euclidean proof, and then you start reasoning about the configuration that you just constructed. So you first observe by side, angle, side. So this stuff is so familiar to me because this is all I've been thinking about for the past 15 years. Do you remember this stuff? Side, angle, side? Okay, so by side, angle, side, you can then infer that this triangle equals that triangle because it's an isosceles triangle, and that by construction, the side AG is equal to AX. So then you get all those equalities there. And those equalities are great because then you can infer that, well, first you can infer that BF is equal to CG by the fact that equals subtracted from equals are equal. And then apply SAS again to get these two angles equal. And then you know that equals added to equals are equals, subtracted from equals are equal, and that gives you the base angles as equal. Okay? All right, so there's text here, there's a diagram here. Euclid was usually, up until maybe 20 years ago, Euclid was thought to be not rigorous because he's using diagrams, that it's kind of vague and intuitive. It helps understanding, but it's not logically rigorous. To make it logically rigorous, you have to do something like a logical analysis. But 20 years ago, a guy named Ken Manders came along and observed that actually the diagrams are used in a systematic way. And he wrote a paper called Euclidian Diagrams. And so here, the diagram is used in 2 points in a way that it needs to be used. You can't get rid of it. It's what's highlighted here, these 2 steps. Now, the reason you need the diagram here in these 2 steps is that you're applying this equal subtracted to equals rule. The first time to segments, the second time to angles. But to know that that rule is being applied correctly, you have to know that the right containment relations. So you're talking about A, B, F here, and you know that, right, so you know that this is equal, that's a terrible drawing. The point is it's equal subtracted to equals. You subtract out, you know this is equal, and you subtract out this is equal as well. And so to make that subtraction, to know that the rule can be applied correctly, it's the analogous thing over here. You have to know that the order relations are right. So that if F was over here, if it was beyond, I'm sorry, not F was beyond, if B was beyond F, the relationships wouldn't be right, so you couldn't understand equal subtracted equals as being applied. Okay, that was a little long there, but is the idea to know that if you can, when you subtract equals from equals, you have to know that the thing you're subtracting is contained in the bigger magnitude. And to know that, you need a diagram. That's the point. Okay. And it's the same idea with the equal subtracted to equals with the angles. Okay, that information is nowhere to be found in the text. You need the diagram to be able to see that the right containment relations hold. Okay. Now, but the point about this information, and this is Manders' insight, is that that information is qualitative. It's in a sense rough. You don't need to take out a measuring stick to realize that those containment relations hold. Okay, you don't have to be precise. It's only what I'm calling here qualitative spatial relations. Manders' term for it is co-exact, as the complement of the exact information in the diagram. Okay, you only need Euclid only, at least for Euclid's proofs, you only need the diagram for these qualitative spatial relations. You might think that, I mean, there's a lot being talked about with this configuration, equal angles and things like that. But those relationships, you need the text to reason it out. But you still need a diagram. For the diagram, you need the diagram to be able to show you how the geometric objects in your configurations relate to one another in a qualitative way, not in an exact way. Okay, so with Manders' analysis, then the picture you get of his proofs is that you have 2 tracks. You have a diagrammatic track, a track where you have the configuration represented in the diagram, and then you have the textual part. And the role of both have very precise roles within the proofs in terms of the information that they hold in the proof, or they hold for the proof. In the diagrammatic track, the point is to record qualitative spatial information, this co-exact information. And then the sentential track is meant to record and show inferences with the exact metric information. Okay. There's a lot more in this paper by Manders, but this is what, as a grad student, I focused in on, and I wanted, because I was at Carnegie Mellon, and at Carnegie Mellon we formalize everything. So I wanted to formalize what this suggests, this analysis suggests that there's actually a formal method behind what Euclid's doing. And what I did in my thesis was to try to flesh that out. Okay, so EU is the system of my thesis, and then I worked with Jeremy Abogad, the professor at Carnegie Mellon, to develop E. So these are both, they're related formal systems, and I'll just treat them as one analysis here. And the idea was to do what I just said I wanted to do. I had like 4 years, this is just a side note, but I had 4 years with the PhD getting nowhere. And then I had the idea of diagrams, and then everything came together. And then I'm not, for 10 years later, I'm still talking about it. Anyway, that's the whole point of this system, is to do what I just said I was looking to do, to create a formalization of Manders' analysis, or to flesh out Manders' analysis in formal terms. So, corresponding to the tracks of Manders' analysis, or the two-track picture of Manders' analysis, there's two basic kinds of symbols. You have the sentential symbols, whose role is to record exact metric information. And then you have the diagrammatic symbols, whose role is to record in proofs to express the qualitative co-exact information. And then you also have to have rules. You want to be able to prove things with these symbols. Okay, so in this account, this is the general form of a Euclidean proposition. It's a conditional. In both the antecedent and the consequent, you have two kinds of symbols. You have the diagrammatic symbols, and you have the sentential symbols. Okay, in the previous slide, they were A. This is supposed to be S1 and S2 there. So here's an example. This is how it's in EU. This is the proposition I just proved for you, or just showed the proof for. All isosceles triangles are equal. So you have the diagrammatic part tells you the co-exact relations you're dealing with. It's just a triangle. It looks like an isosceles triangle, but it doesn't have to. It just has to be a triangle. And this is telling you that these two sides are equal. And given the same triangle, then you know that the base angles are equal. Okay? And within the system, and I think also within Euclid's elements, I think this is, you can debate how accurate the analysis is, but I think this corresponds directly to something you see in the elements. For Euclid, the significance of his proofs are that they actually become rules of inferences in later proof. And you saw that. I applied SAS in the proof. And the proof that all isosceles triangles have equal base angles is used later, but it's a direct application. It really becomes, in effect, a rule of inference. Okay, so now back to the question of individuating Euclid's theorems. With this analysis, you get an explanation for why certain things become propositions and others don't. This form, it corresponds pretty closely to the logical form here is pretty straightforward. It's just a for all exists statement where the propositional component is just a conditional like this. Okay. And it's an exist statement if you're constructing something, otherwise it's going to be what's a theorem. But the point is then that here's all possible logical statements that you could, within the axiomatization, you can think of all possible logical consequences of the axiom. But this form here shows that why these certain statements of a certain logical form are the ones regarding those theorems. Also, the idea that I was just referring to, that theorems are rules of inference, I think explains why you don't have conjunctions as just arbitrary conjunctions of propositions regarding these theorems, because it doesn't make sense to have a conjunction of rules of inference. Okay, so that still, this might not seem so philosophically relevant because it's just talking about maybe you could look at this one. Natural way to look at this is just a conventional way to present geometry. It's just Euclid's conventional way. There's certain arbitrary choices of how you want to present information. The logical analysis gives you the information in itself, and so this analysis just shows. One way to look at this is just the analysis with the diagrams is just showing that Euclid has a very idiosyncratic way to present propositions. And it's actually limiting because you could actually have a more general view, and maybe you would want that. Okay, so this leads to the question then, does this have any epistemological significance, this analysis? And so the no answer is the kind of the answer I was just referring to here. What matters about mathematical knowledge generally and Euclid's elementary geometry specifically is its content, the actual, the content as revealed by a logical analysis, the propositions. And the particular notation that you use to express this content has no epistemological significance. So a yes answer, and that's the one I'm going to try to defend or convince you of or argue that what I'm arguing is that if you take the content of one of Euclid's diagrammatic proofs and then you present it in a different notation, you destroy the proof. And so the individuation of theorems, the thing that I was just talking about, actually reflects a constraint on how you develop the geometric knowledge, that it's not really a generalization of the knowledge. You're doing something different when you do the logical analysis. You're changing the knowledge in some essential way. So that's the idea. Again, it's not really a widely held idea. Usually notation is thought to be merely notation, nothing that, it's like font. You could use red font, you don't use red font too much, but you could use gray font, you could use Times New Roman. Anyway, the idea is that notation is analogous to that. It's not really important to the proof itself. So, to argue for a non-conventional view, I'm going to go to Wittgenstein, the person you might want to go to. But what he says in section 3 of Remarks of Foundations of Mathematics relates directly to what I want to say. So that's what I want to say what he wants to say here. If you have a proof path, this is in section 3, this is his second paragraph. So he says this right away in section 3, and he tries to develop it. And he explores the idea and tries to figure out why he believes this in the rest of the section. So this is his main point here, is if you have a proof pattern that cannot be taken in, and by a change of notation, you change it into one that can be taken in, then you're producing a proof where there was none before. So what he's doing, he's tying a mathematical proof to its concrete presentation. And he's in particular interested in the capacity of this concrete presentation to be taken in. And what does that mean exactly? You get an idea of what it means when you look at the examples he considers later in this section. So what he spends a lot of time thinking about is a contrast between arithmetical identities, very simple arithmetical identities that you present with Arabic numerals, and how you can give a logical analysis or a logical presentation of such identities as a tautology. Okay, so this is in logical notation here. What this is saying is that you have two unique xy's such that they satisfy xy. But the point, well, part of Wittgenstein's point is he doesn't, in this notation, the word, or there's nothing representing two. You just have x and y, where x satisfies f, y satisfies x, and then this means that x and y aren't equal. It's a similar phrase here, and then, or it's a similar proposition here, similar content being expressed, and this is saying no f's a g. So if you have all that, then you know this. You know that you have these variables satisfied at this junction here. So this is 2 plus 3 equals 5 in a logical analysis. Do you see how? If you haven't seen this before, do you see it? No? So his whole point is to to compare or contrast the effectiveness of this notation with this notation. He's worried about how we take these symbols in. And it's not, once you consider the question, it's pretty obvious what the once you look at the idea of taking symbols in, it's pretty obvious what you're going to say about these two different ways of representing arithmetical identities. I mean, with 2 + 3 = 5, you can get something that you can fit on a page. But with, you don't have to go much higher with the numbers, with the arithmetical sums that you're dealing with. Like 27 + 16 = 43, when you get things that are just massive. And this isn't that equation. This is just 16. This is how you represent 16 if you're going to try to represent this as a tautology in logic. Okay? So that's ungodly. That's a mess, right? And that's his point. One term he uses, at least in the translation, so I don't know German, so I don't know what he said. This is all from the translation. But this term of characteristic visual shape, that to work with the symbolism, you need to be able to identify a distinctive visual character to it, or characteristic visual shape. We can just keep it his term to convey the idea. All right, so this isn't that effective, I guess, as a way to illustrate this, because this is under that, and so you know that this is a smaller number, right? But if you were to try to write 16 or 27 + 16, 27 + 16, if you had the 16 there at the top, you wouldn't know if it was different from 15 just by looking at it. Okay, that's his point. That you can't. If you're actually looking at the sum, you won't be able. This is roughly more than 10. You know that when you look at it. And so if you would see if you try to represent this as a tautology, it would take up a lot of the page, and you would know that they're fairly big numbers. And maybe with more experience, you get an idea of roughly what expressions like this, what kind of numbers are being represented. But the point is, you wouldn't know precisely, in the same way that you would know precisely that you're dealing with 16 in the Arabic numeral notation. Okay, so one thing you could say, and Wittgenstein recognizes this in the remarks on the foundations of mathematics, one thing you could say is, well, you could just count the variables, okay? And then you see how the identity is proved. Do you know what he says to that? Do you have an idea what you could say to that? How you could respond? Just trying to get participation here. But anyway, his point is just that, well, first of all, I don't say it here, but one immediate comment is you're trying to provide, one thing he's interested that I'm not really going to concentrate too much on, but he's interested in these kinds of analyses as a foundation for arithmetic, as a way to kind of explain what arithmetic is about. And so one of his responses is that, well, if you're going to start counting variables in a proof of arithmetic, you're using arithmetic in your proof of arithmetic. The counting is a numerical technique. So there's a circularity there. I'm not so much concentrating on that aspect of it. I'm just concentrating on looking at Wittgenstein here in the remarks as a way of looking at the concept of what a proof is and what are the conditions for a notation to communicate a proof. And so, and this is also in there, I think, this idea. Once you require additional techniques to figure out what your proof is saying, the symbolism stops functioning as an effective proof symbolism. So I think one thing he says is that if you have to do a physical investigation of the proof, it's no longer a proof. So counting is kind of like a physical investigation. You have to make sure you're at the right place as you're counting. What you need, so this is kind of illustrating, I think, not illustrating, but in these considerations of Wittgenstein, something that's coming out is one of his, he doesn't lay it out, but I think one of his conditions for an effective symbolism is that you have to be able to, you have to just read it. It has to be readable. And so it has to be immediate what the content is. And you don't, once you have to use other techniques to figure out the content, it's no longer a proof symbolism. This point the same general point applies to another thing you might think that you could do, which would be to represent this to figure out some notational convention for representing what's at the top. So you can, do you see how this might abbreviate that at the top? But his point then is saying, well, you're using Arabic numerals. You're just using Arabic numerals here with all this wrapping around it. That's this term, right? So really the notation, the operative notation here is still Arabic numerals if you're going to do that. Okay.
That's English versus bars.
Yeah, he did bars as well.
Yeah.
You're right. So yeah, one thing he also talks about this as representing pi, and this representing, I don't know what that represents. I didn't count. That's part of the point, right? Yeah. So, but it would, 8, okay? So he considers those as well. But the point is, though, if once you have the 8, you know it's the 8 because you have the circle. It has a characteristic visual shape. But this has a characteristic visual shape, but it's not distinguished. Its characteristic visual shape is not really anything different from 7 and 9. That's his point. Okay, so something in the background, this is the way I'm going to understand it with what's going on in this section 3, is that you have to take into account what human beings can perceive, what they can distinguish in symbols. So there's a constraint. And I'm saying this in the background of a lot of philosophical discussions where you idealize people who read symbolisms. If you're going to do a logical analysis and you're going to understand a logical theory as having a syntax, many of the things that actually are going to be represented in the syntax are not readable. Like the simple propositions, like just in elementary geometry, if you're going to try to represent something like equal angles in Tarski's axiomatization of elementary geometry, it's if you want to represent it in terms of the primitives, it's going to be a really long expression. Okay, and so the idea that it's just elementary geometry is just a sequence of logical formula, it's an idealization because we can't really read most of the things that you would actually need to represent the content of the theory. But people don't care. I mean, also with Gödel's famous theorem, right? The the incompleteness theorems. I mean, he has a lot of famous theorems, Gödel. But the big one, the incompleteness theorem, the idea is that there's a syntax there. And that syntax is supposed to be things that you write on a piece of paper. But the Gödel sentence is like a book. You're trying to actually write the Gödel sentence and unpack the whole thing. It's just unreadable. It's not something a human being can take in. But no one cares, in a sense. I mean, with Gödel's theorem, I think there's reason to not care because you're establishing a limiting result, a negative result about what formalism can do. So you might as well idealize. But it's a general idea in just philosophy of mathematics, or at least philosophy of mathematics that wants to look at things from a logical perspective, to just dismiss the kind of concerns that you see in section 3 as just merely psychological. So merely notational is connected a lot to merely psychological, because one way to understand different notations, or what makes one notation better than others, well, it seems like you have to go to human psychology. And if you're going to do that, well, then you're just treading on to something that really doesn't have to do with the objectivity of mathematics. Okay? So that all I meant here is just Wittgenstein is firmly standing against this idea that you have to take into account what human beings can recognize or not recognize. Because we could conceive of some being in some science fiction fantasy that can distinguish that as 8 and not 7, right? The second expression there in the bottom. But for Wittgenstein, he doesn't care about that. That's just a silly consideration. We have to really understand proof. to really understand what is going on with mathematical proof, you have to take into account what people actually can take in and not take in the symbols. So, I mean, this is all. There's a quote that I think really encapsulates this really nicely. It's in paragraph 53 of section 3. So it's one of those times where he's talking with an opponent, as he often does. So he's talking to someone who's representing the idea that no, a logical analysis actually gives us the essence of arithmetic. So that's the person. The first quote is from someone who's expressing that view. So the reference to the secondary system is the Arabic numerals. The reference to the primary system is the logical symbolism. So this guy says, but every step in the secondary system, we can imagine that could be taken in the primary one too. And then Wittgenstein's response is that, well, that's just it. We can imagine that it can be done without doing it. No one does it. No one works in Russell's Principia Mathematica. It's unworkable. It's in a very real sense infeasible. For a very obvious reason. You can't tell 16 variables from 15 variables in a list. Okay, so that's the Wittgenstein portion of the talk. I want to now apply this back to Euclid's proposition 33. But it really is a radical idea, and it's the concept of he's tying the concept of a proof to how it's presented, and that's not. It's kind of hard to theorize about that actually. This is a very small attempt to try to do that. Because with logic, one thing that's great about it is you know exactly what you're talking about with the formal syntax. But how you're going to individuate or identify different presentations of proof, that's tricky. But one thing you can do, at least I think you can contrast, as Wittgenstein did, you can contrast different presentations and then make some observations. So that's my strategy here. The same approach Wittgenstein had in section 3. You take two different presentations of a certain elementary proof, and then you see if you can say something about them. So I want to consider the beginning. I'm not going to consider the whole proof of proposition 33. I just want to consider the beginning of it. And specifically, I don't even want to just consider the beginning. I just want one step in proposition 133. In the beginning, there's a certain previously proved proposition applied. So the way the proof works here, if you remember what is being proved is that we know that these two lines are parallel and equal. We want to prove that these two are parallel and equal. And so you start with these two lines, you join these two endpoints here. That's what's being talked about here. And then he joins the diagonal. And this next step is the one I want to concentrate on. He applies proposition 129. What this proposition says, this is a review of your high school geometry. This is, what we say in English is alternate interior angles. If you have this configuration where these are parallel, you know that these two angles are equal. Okay, so that's the geometric fact that's being applied at the beginning of 133 that I want to concentrate on. I take this application to have two steps. So I'm looking at it not from the point of view of someone actually discovering the proof or coming up with the proof, just someone reading the proof and understanding that it's a proof. So it's a reader of a proof I'm concerned with. And the activities or the tasks involved in going through the steps of the proof and understanding it's correct. And so in particular, this step. Now this step I take to have two subcomponents or two subtasks. The first one is just to recognize that the conditions of the theorem are satisfied within the information you have already presented. Okay, that would be the first thing. The second thing is once you realize that the conditions are realized, but they're realized in a particular way, and you want to then apply the rule in the particular way that the conditions are realized. Okay, so this might become more clear in a second. What I mean by these two tasks, I'm going to go through it both with a sentential notation, or both with a diagrammatic notation and a sentential notation. But my claim is it's just the same as Wittgenstein's. The claim Wittgenstein made relative to logical notation as a proof, as a way to prove arithmetic sums versus just the normal Arabic numerals. That when you try to do all this in purely sentential notation, you get something analogous to what was going on in the case that, or the contrast that Wittgenstein was talking about, or making, the contrast he was making. Okay. So this is my picture of a universal reader. He's reading the proof in a diagram with the diagrammatic symbols. Okay, so this is the proof context. This is the information with both diagrams and sentences. Euclid's proofs are 2 tracks according to Mander, so you have both kinds of symbols, but the crucial thing is the diagram. That's the one I want to concentrate on. And this is the theorem, or proposition 129, expressed with diagrams as well. Okay, so what this guy has to do, he has to recognize that these conditions are present here. That's the first task. And the second task is then to produce whatever corresponds to this here. Okay? So first, recognizing that the conditions of the theorem are satisfied. The story I'm going to tell is that, well, you understand 129 in terms of the diagrammatic notation. Okay, so you recognize that this shape is present in the diagram. And the shape down here could be represented in a variety of ways, given the fact that it's only coexact or qualitative information that's being represented. So you could also represent the conditions like that. Like that. The point is that these are coexact equivalent to that. But you can see that, you can recognize that shape. And then once you recognize that shape, and then you also need the sentential information, or you need the exact information. You need to know that those two things are parallel. So you know that it's the things at the top of the shape, the top of this shape here that are parallel, and you see that what corresponds to that over here is said to be parallel. So we're good. The conditions of the theorem apply. And then the second task is to produce the angle that corresponds to that. Okay, so you have to verify it's a correct application. I think we need to realize that that's correct, or not realize, this guy has to recognize that this is correct. This is the correct way to apply this. And my story then would be that, well, you see that this angle, you actually, I would say that you don't even understand it in terms of this expression. You actually understand it as these two angles is equal. And then you have the indices here that tell you what you should write. And so you look up here, you know that it's these two angles, and then that determines the indices. Okay? But this is, I'm concentrating on this because how the variables work out is going to be, or come up with this intentional case. But here, the way the variables work out is through the picture. Okay. This is how it is in purely sentential notation. Okay, so this is the coexact information of the diagram. This is how you can represent it in terms of sentences. This is actually how the formal system E does it. So we have E, U, and E, and they both give an analysis of how diagrams work in Euclid's Elements. The system E actually represents the diagrammatic information as sentences, so it's not really diagrams. But it's the same, it's the diagrammatic information. So these are taken from the system E, these primitives. And, well, no, actually, these are taken from E, but this is not. But anyway, we're just saying that this tells us that the 4 points that you have, that they're not collinear. Okay? This is telling you that they all lie on the sides in the right way. Okay? This is telling us that the diagonal splits things in the way that you can see directly here. And this is the same statement about parallelism. Okay? And so that's the proof context. That's the information in the proof. This is how 129 is expressed in terms of sentences. You can actually present the conditions pretty quickly of the shape of alternate equal angles. And then this is the output. Okay. All right, so looking at this now from the point of view of these two tasks, you first want to recognize with this formalism that the conditions of the theorem are satisfied. First, are you with me? Okay. First, you want to know that you actually have the same relation. And you do, and that's actually not so hard. That's immediate. If this was only that, my point wouldn't hold if this is the only thing that you have to look at. But you have to actually look at more than just the fact that you have this relation. You have the negation of same side, and you have is parallel to. It's more that you have to look at. Specifically, you have to look at the pattern of the variables match, right? Because you could have AC same side, AC same side, DB, and this would have the same. This would also be a negation of same side, but it wouldn't work because the variables don't match. So yeah, part of the task here, and this is the hard part, is if you're going to do with this notation, is actually to see that the variables match. Okay. And I'm not saying you can't do it, but what I'm saying is, my point is that what you would have to do it would be analogous to counting variables in the Wittgensteinian case. You'd have to have some new technique where you very carefully match things up and verify it all holds. You can't see it immediately. And that's part of this Wittgenstein's criteria here, is that you can see it immediately. We can see, I think we can, with simple configurations of variables, actually see that the conditions are satisfied. So you have transitivity. So suppose A less than B and B less than C. We can see that that realizes the transitivity, the conditions of transitivity, right? I would hope, right? But with more complicated situations, you start getting more variables, more complicated patterns, you lose the ability to see it right away. In the same way, I mean, this is a cognitive claim here, and you might want to press me on this, and I don't have any experimental results to verify this, so I'm just relying on your intuition here. This is, I guess, a weak point. Not a weak point, but it's a place where I'm just making a bold claim here, based on your reaction to what I'm showing you. That once you lose the ability to just read off the pattern of the variables with more complicated patterns like this. And that's key. It's worse, really, to actually produce what corresponds to these variables. Again, you would have to make a table and make sure that this variable connects to that variable. And then what variables do I need to produce here, given that correspondence? You have to go through all that. And you could say maybe there's beings out there that don't have to do that. They can see it right away. So this is where I'm claiming that there's a cognitive limitation. And for this reason, the proof is destroyed. Okay. So I'm bringing everything I said together now, just in this slide. So my claim would be that with 129, you have this characteristic shape. That gives you the ability to make the correspondence between the variables. And you understand the theorem in terms of this shape, really. And that is what allows you to deal with the variables in a easy way. But if you remove the diagram, you have to recognize things like that this pattern is the same as that pattern. Okay, I can't say that they're the same. Maybe you can. But again, this is a place where the work has to become a little sharper to figure out what cognitive faculties here are involved that make it hard to actually see that this is the same pattern. Okay, so then you have to just not only have to recognize that these two realize the same pattern, you also have to be able to produce, once you realize that they have the same pattern, you have to produce these two sequences of variables. And it's not that you can't do it, but if you were to do it, you would have a different proof. Okay, you have the diagrammatic proof, it's one step. In a purely sentential notation, the proof would expand. And so there's something else going on here. There's a certain idea of individuation of proofs, or what makes one proof different from another. the fact that you have different basic steps. So one other thing that has to be worked out here is what's a basic step. But I would claim that you have more basic steps here with this intentional notation, so you have a different proof. Okay. All right, so I'm done. Did I fill up my time? Yeah, that's enough. So, but I'm not completely done. I have 3 more bullet points in the conclusion here. So I think I've just shown you one case here, but you have rules and theorems being applied throughout the elements, where part of the information you need to know that the theorem is being applied correctly comes from the diagram. And an analysis similar to the one I did here, I'm pretty sure, I'm very, 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 very confident can be carried out with those other things. Because it's just, again, the way you represent it sententially is just in terms of a configuration, and you just have a lot of variables, and you just have to figure out the pattern of the variables. So this then would say that you need the diagrams for the proofs. The diagrams are essential to the proofs. Even though you can give an analysis where you understand exactly what the diagrams are in terms of propositions. So it's the notation, it's diagrams as notational. One reason to emphasize this point is that diagrams were often thought to be maybe like something non-logical. Well, I mean, I'm saying that they have a non-logical role here, but one idea with diagrams is that they give you some kind of non-analytic information, like synthetic, intuitive information. I'm not saying that at all, because you can give a logical analysis to the information. And it's the same, you can give a logical analysis to the information held by the diagram. So if you're worried about the synthetic versus the analytic, and the diagram somehow give you something intuitive and synthetic, I'm not saying that. I'm saying that diagrams give us a particular way to represent certain informations to make logical deductions, and a very effective way for geometry. And you lose that, the proofs become unworkable if you try to present them intentionally. All right, so then you see diagrams throughout mathematics, not just geometry, and I think that this might help explain how you see diagrams, or why diagrams are used in category theory, for instance. That's what Sylvia de Toffoli is looking at in a paper of hers. Carter has another example she looks at where diagrams are used in work of analysis. And I think if you could tell a similar story with those cases. I think, well, there's at least potential. So that's something else you can do. Finally, the final point here, everything here has been looking at concrete symbols, diagrams, Arabic numerals, logical formalism. So there might be a lot that there's a lot it doesn't cover in mathematics and mathematical proof, because advanced mathematical proof is also very conceptual. But my intuition here is that similar points might apply to defined concepts. So in mathematics, if you learn mathematics, it's filled with defined concepts. These proofs are structured around defined concepts. But from a foundational point of view, defined concepts aren't really real, because you just have your primitives and you define everything in terms of those primitives. And in principle, you can present everything in terms of the primitives, and the defined concepts just disappear. So, but I think if you're going to have the same kind of worries about readability or intelligibility of proofs, I think similar points might apply to defined concepts. And that's just something else I want to say here at the end. Thank you very much for your attention.
I'm not sure I understood correctly your main point here. You're saying that the main difference between diagrammatic proofs and sentential proofs is one of effectiveness, that diagrammatic proofs are more effective in that there's some steps that we can see immediately, whereas you have to take several steps. Or are you saying that the sentential proof is not a proof at all, or it's a different proof? So I'm not really
No,
sure.
right. Okay. Yeah, I didn't make that clear. So, and this has to do with the issue also of how you individuate proofs, because many times a proof presentation has steps that are implicit that the reader is understood to supply on their own. And so back to the first slide. So the most dramatic way of saying it is that the sentential proof is not a proof. And if you don't assume that the reader supplies his own steps, then this is not a proof. Okay? Because you can't, from this information, immediately make the steps. The reader has to actually supply certain steps, namely coordinating the variables in a certain way. Now you could say it is a proof if you're assuming someone can, the reader is allowed to apply or supply steps. But the point would be that it's a different proof, and it's radically different. You need actually new concepts, new techniques of coordinating variables. And so the weaker claim that's a different proof would then assume that the reader applies different, or not applies, just uses different techniques to fill in the details. And part of the point is that this is okay. I mean, one way to look at, you don't have it rigorous until it's all sentential, and that this is just implicit having those steps. Part of the point here is this is okay as it is. This is a perfect way to represent the information. And it's also, and that way of representing the information is essential to what it is as a proof. So that's the exploration of the concept of proof here in a way. Does that help?
So could you fully analyze the diagrammatic proof in terms of sentential proof?
Well, yeah.
You could in principle do that. There wouldn't be any, so that there wouldn't be any missing steps.
Apart from all medical limitations, as customers say.
So that, well, I mean, actually, that's the idea of this. That this is the purely sentential analysis. And so the point would be that you can't be, the point I was trying to argue for is that you can't look at this and just apply this directly. It's a cognitive point. In the same way that you can't tell 7 strokes from 8 strokes. That's the claim. And if you buy Wittgenstein's point that notation is part of what a proof is, you don't have to buy the point. But if you buy that point, it applies here as well.
In the beginning, you said that we need the diagram to get the right containment relations. Now you're saying that you could get the right containment relations without the diagrams.
Okay, so yeah, when I said it in the beginning, when I said you need the diagram, I meant if you're just looking at Euclid's proofs. I wasn't making the dramatic claim that you can't get it any other way. I didn't mean that. I understand how you might understand it that way, but I didn't mean that.
Oh,
Well, thank you for very nice talk. One thing which I found particularly neat in your comparison of what you're claiming about Euclid and Wittgenstein's discussion of process primitive notation in section 3 of the remarks is the fact that Wittgenstein's discussion of process notation belongs in the framework of an assault on logicism. Therefore, the idea that the proof could be, in principle, as always rendered in purely sentential form.
Right.
Now, the interesting thing is that the steps which, as you say, the reader must supply are not representable in primitive notation. Unless you think of some beings which have cognitive capacities which we totally lack, blah, blah, blah.
Right.
Now I wonder, this is Wittgenstein's requirement of what he calls severability.
Yeah, I didn't use that term, but yeah.
Proofs in the process primitive notation are not so variable.
Right.
The other twist that the equivalence between the original non-primitive notation, 2 plus 3 equals 5, or whatever it is, and the rendered primitive notation are themselves not representable inside the process system.
Right.
It's something which you say about the system
Yeah.
in a meta language.
Right.
Meta language, not a higher order proposition inside the system of
Right.
lower order propositions.
Right.
Now I wonder how all this connects with truly unsurveyable examples of mathematical proofs, like say the four-point theory.
Okay. How that observation? Right. It's a different situation because, I mean, there's a relation, but because surveyability is in play here. But this is something what we're talking about here is something only philosophers worry about. It's not, mathematicians wouldn't care about this because they would just look at the diagrammatic proof and they're fine with it.
Yeah, sure.
So, but one difference is that with the four-color theorem, this is actually a roadblock to surveyability that the mathematics forced you into. It's not because you had some principled idea of what the mathematics how the mathematics should be presented. And to whether or not this applies to this, I'd have to talk to Giselle more because I'm not familiar with the details of that proof. I know that you had a lot of cases to work through, right? That's how it works. And there's no way you can't verify that these cases you can't observe what you need to observe mathematically with all these cases by hand. That's part of the point, right? One quick statement would just be that there's no notation that allows you to make these verifications by hand. And you need to have the computer do the computation. The one analogous thing might be just that, the variable matching I'm talking about here is very easy for a computer, right? It's just not something that if you're talking about notation as things you write on a paper and understanding proof through symbols on a piece of paper, you can't do this, or you can do the variable matching, but it's just awkward and it's like walking through a swamp, whereas with the diagram, it's just right away. And so there might be an analogy there as well, as this would be something that you could really, applying it in a purely intentional way, something a computer could do really easily. And so you have that ease with the four-color theorem as well. That'd be the one connection. Right? As much as I can say about that.
I have a follow-up question. Thank you for your comment. I like the way you try to bring teaching side to the suggestion. But don't you think that the possibility of building machines that could, for example, counting the number of the variables in a decision formula, did that make those human limitations
Superfluous or not? Right. Yeah, so what you have to, something I haven't done here, but you have to argue for the idea that if you're going to give a philosophy of mathematics or analyze mathematics, you want to analyze it how people actually work with symbols. And that's your data. That's the thing you're trying to explain or characterize. And you could come in from a foundational perspective, the Frege and Russell perspective, where you have this principled idea and you want to figure out if arithmetic is synthetic or analytic, and you have a logical analysis and you show what the concepts it's based on. And if that's your perspective, then the fact that you can have a computer work it all out will verify something for you. But so something in the background here, but you have to, I guess maybe I'm not embarrassed, but I didn't feel like arguing for it. But something you would actually have to argue. I'm not embarrassed by it. I believe in it, but I didn't want to argue for it. Something you have to argue for is that with this kind of approach to philosophy of mathematics, you're worried about what we're actually doing with the symbols, and that will then constrain the kind of abstractions you make and how you identify what a piece of mathematics is and what's a piece of related but different mathematics. So one thing Wittgenstein would say is that once you do it all on a computer, well, it's a related piece of mathematics, but it's not the same mathematics because you don't have human beings interacting with symbols in the same way or engaging with the symbols. That would be, but if you don't buy that, then none of this is interesting, right? If you don't want to try to understand mathematics from that point of view of actually how human beings interact with symbols, then you should have done something else this afternoon. Does that make sense? Yes, which one?
So Rogério again, and then Rodrigo.
This is something I'm curious about. So your talk was mostly concerned about proofs, but what would you have to say about the stronger claim that there are some kinds of spatial information that cannot be conveyed in purely logical terms. So that would have some consequences to what you have to say, and might affect the equivalence of these two kinds of proofs. And in particular, I've read two authors that have made similar claims. One was Kant when talking about incongruent counterparts. He says, so you've got a right hand and a left hand, and if you give a purely conceptual description of a hand, you wouldn't be able to tell whether it's a right or a left hand. And another author who has said something similar was Quine when arguing against Carnap's off-ball. He says, well, if you're going to construct the physical world out of your psychological world, then you need to project points into space. So X, Y, Z is at so and so. And Quine says, oh, this is at is not, it cannot be conveyed in purely logical terms. This is spatial, temporal, spatial information that's not built into Carnap's logical notation. This is one of the reasons why Carnap gave up on the outfall. So those two authors have argued that there are some kinds of spatial information that cannot be conveyed in purely logical terms. So if that's true, then perhaps you might have some diagrammatic proofs involving those kinds of information that cannot be that do not have a counterpart.
Yeah, well, I think the first point, the Kantian observation with orientation. So the incongruent counterparts has to do with orientation. I agree with that. You can't record that logically. You can record that you have different orientations, but you can't distinguish clockwise from counterclockwise. How much that plays a role in proofs, I'm not sure. I think there is a point that there's content, but how much it plays a role in the inferences, because you just have to know it's one orientation versus the other in the actual inferences. But yeah, I think there is a point there, but that's away from the proofs there.
Right, but isn't that just because you're dealing with proofs about symmetrical objects where orientation plays no part? If you had proofs regarding asymmetrical objects, then that information would play a crucial part.
Yeah. Well, what I've noticed with same side, for instance, or you could in a way talk about counterclockwise and distinguish, not same side, I guess. In dealing with the primitives with same side, one thing that we thought maybe to do is not say same side, but say on the left side, right? But if you formalize that in terms of sentences, being on the left side could just as well apply to being on the right side. It just would be different from whatever this is. So there's a way that orientation information could be relevant, but in a proof. But you wouldn't know if you're dealing with this orientation or this orientation. You just know it would be different from the other. So that's what's behind me saying that you don't really need it in proofs. In a way you do, but you just need to know you have two and one's different from the other. And so I still think there's content there. I agree with Kant that there's content to the difference between these two things that's not captured by just saying you have two different orientations. But then how that pops up in the proofs isn't. You need it for applications, right? You need to be able to apply to say that you're on the right side so that two people know what you're talking about. But if you're just going to look at a proof or formalize a proof, you don't need to make the difference. So that's what I'd say about with Kant. The Quine's interesting. I wasn't aware of that, so I'm very happy to know that was instrumental with his criticism of Carnap. But yeah, I guess I would say again that has to do with application. I'm a pure mathematics guy, I guess pure geometry guy. But I think if you come to Santa Maria, I give a talk on a certain kind of semantics for geometry, where it takes into account spatial content. I'm using Etchemendy to say it's logical consequence, but depending on how you understand logical consequence, you understand it, if you don't want to use Etchemendy, you could also understand what I'm saying as a way of a spatial kind of consequence. It's not logical consequence anymore. And I think you can come up with a story like that where it's not logical consequence in the sense of first order logic and logical constants. So that to say that something is a consequence of premises, you take into account the spatial content of the premises. So I think there's a story that could be said there as well. So it's kind of in the ballpark of what you're saying. So I thought I'd make an advertisement for my talk based on that.
Just a remark about the Cantor example. We know now that as we claim the Felix Klein proved, whatever objects are to common counterpart in the space of n dimension, the dimensions are congruent in the n plus 1 dimensional space. Like the surface of the right and the left hand in the plane of the yeah.
But
People say I can put a globe with the right hand in the left hand by turning it through a 4-dimensional space.
well, sure, right. But we live
Sorry,
in
not-
Wittgenstein said that, really?
Yeah.
That's surprising.
Tractatus.
Oh, in the Tractatus, it's the earlier. But because it's surprising Wittgenstein said it because that's like a fourth dimension. What the hell? We don't live in fourth dimension. Right? Okay. So explain. Right.
Rodrigo?
Oh, first, thank you for the very interesting presentation. It's a real question with arithmetical topic that I think maybe some things you said can apply. I have what do you think about it?
Okay.
Question.
Okay.
Well, famously in Principia Mathematica, Russell took and White they took 900 pages to prove that 2 plus 2 equals 4, right? So, someone could say, well, that's no proof because I have to understand that I have to have an intuitive previous understanding of arithmetic to even follow the proof.
Right.
And that's even speaking from the perspective of someone sympathetic to logicism, that is a plausible position. But one could take the proof in Principia as not as an attempt to provide a foundation for our belief that 2 plus 2 equals 4, but as a piece of mathematics in itself, as what we could call working regressive mathematics. And then the mathematical object we are working is not the point 2 plus 2 equals 4, but the logical analysis itself of the proof. And my question is, would you be fine with that? And would you think that even in this taking this more modest approach to the logical analysis, if we can see a theoretical gain
Sure.
from that perspective?
Yeah, I would say that there's a theoretical gain. Even Wittgenstein, I mean, I hesitate to say I know what he's saying exactly, but he does say that what you're doing, what Russell's doing, is relating one piece of mathematics to another piece of mathematics. He doesn't deny that, as far as I can see. It's just he's really directed against the foundational value of the logical analysis, that it actually somehow grounds the mathematics. And I didn't touch on that at all. But in investigating that question, he dealt with these issues of surveyability, which is what I was drawing on. Just myself, I think, there's definitely something revealed by logical analysis. I don't think the diagrammatic work would have been possible without Hilbert's logical analysis, because he recognized that you have betweenness. The way Hilbert, and then before him Pasch, axiomatized geometry, gave a logical analysis, really helped. I don't think Manders could have done what he did without having Hilbert and Pasch in the background, because they showed us what the diagram was interesting or important for. This order information, this qualitative order information, which was just kind of people did it, but it wasn't made explicit. So the point is logical analysis can bring out stuff that's important and interesting. So I agree.
You could see as complementary activities that mathematician could do.
Sure.
You could learn things about each activity from
Right.
another. Right?
No, right. Yeah, I think the one thing is just that but they're different proofs, they're different mathematics, and you don't need the logical analysis for the proof.
Yeah, sure.
Yeah, that would be the weaker point. But yeah, I don't. Yeah, this isn't meant to. I think Wittgenstein's hostile law idea of logical analysis is just pointless. But I'm not. I guess I wouldn't. Yeah, I think there's things to be gained.
Any more questions? So thank you, John.
Thank you. Thanks you for the very good question.